So today we're going to start driven motion. Here's the idea with driven motion. Again, you have your mass, and you have some object that is on that spring. So you have a spring, with an object on it. The object moves, so it can be pushed up. It might be pulled down. So that we've seen before. Here's what's different. There is some external force that is moving. So the spring, whatever it's attached to, there's some external force that's moving that attachment. So it's going to be similar to what we've done before. We're going to look at interpretations, and then we're going to solve. Here is the beginning equation. So we have m times the second derivative of x with respect to t, like yesterday, is equal to negative kx subtract beta times dx dt. That's exactly what we saw yesterday. Here's where that external force comes into play. We get plus f of t. So that is our external force. Okay, so generally what you're going to do is you're going to put it in standard form. I'm going to move these two over to one side. So I get m times x double prime plus beta times x prime plus kx is equal to f of t. This is where I would suggest that you start every time. Or if you want to remember one that's a little more complicated, you can also put this in standard form by dividing by n. M, so you would get x double prime, beta divided by m. Yesterday we made that 2 lambda. That k divided by m, we made omega squared. This little f gets divided by m also, and generally we put then big F of t. Remembering that that's equal to little f of t divided by m. I'm not going to go over how to find m or how to find beta or how to find k. That's exactly what we've done the past 2 days. So that one I'm not going to go over. We're just going to go over solving this. So here's our first example. 1/5 x double prime plus 1.2 dx dt plus 2x is equal to 5 cosine of 4t. With the initial conditions, x of 0 equals 1/2, x prime of 0 equals 0. Okay. We're going to talk about what all of these mean before we start solving it. What does this 1/5 represent? Right, the mass. What does that 1.2 represent? Or what did it represent yesterday at least? The damping force. 2 is the spring constant. What is that 5 cosine of 4t? The external force. X of 0 equals 1/2. Okay, so the starting position is half a unit below equilibrium. What does this represent? The x prime of 0 equals 0. Released from rest. Bless you. Why is this significantly more tedious to solve than the previous 2 that we've looked at? It's non-homogeneous. Okay, we're going to start by multiplying by 5 so that we get this in standard form. So we get x double prime, add 6x prime, add 10x is equal to 25 cosine of 4t. Throwback to our last unit, how do you solve a non-homogeneous linear differential equation? Okay, solve the homogeneous first. Sure, we can do that. So auxiliary equation is m squared plus 6m, add 10 is equal to 0. Unfortunately, that does not factor, so you're going to have to do the quadratic formula. We get negative 6 plus or minus the square root of 6 squared minus 4 times 10 all over 2. Which is negative 6 plus or minus the square root of negative 4 all over 2. So negative 6 plus or minus 2i all over 2. So we get negative 3 plus or minus I. Now, if we remember, for a non-homogeneous equation, you're going to get a complementary solution and a particular solution. This helps us find the complementary solution. Be careful with your notation. Remember that it's x and not y. So that negative 3 will be e to the negative 3t. And then we get c1 cosine of t plus c2 sine of t. Now, we need to take that force into account to find the particular solution. What are the two methods that we have to solve for the non-homogeneous, for the particular solution? Undetermined coefficients, variation of parameters. Yeah. In easier terms, we can use the annihilator method, or we can use the Wronskian. I chose to do annihilator. Is that okay?
Yes.
Okay, so if we apply the annihilator here, the left side, this will be d squared plus 6d plus 10. How do I annihilate 25 cosine of 4t? D squared plus 16. Applying that to x will give me 0. So remember, this represents the complementary solution. This one will represent the particular solution. So our general solution will be the complementary at the particular. Complementary is that e to the negative 3t, c1 cosine of t plus c2 sine of t. If we set this equal to 0, we get plus or minus 4i. So our particular solution will be c3 cosine of 4t plus c4 sine of 4t. So that's the one that I want to focus on. I'm going to change the c3 and c4 to a and b. So if you remember, ultimately we're going to want to go back to the differential equation. So we're going to need the first derivative and the second derivative. We get negative 4a sine of 4t plus 4b cosine of 4t. Bless you. Second derivative will give us negative 16a cosine of 4t minus 16b sine of 4t. Okay, so then we need to substitute into that differential equation. So we're going to start with the second derivative. We get negative 16a cosine of 4t minus 16b sine of 4t plus 6 times the first derivative. So that'll be negative 24a sine of 4t plus 24b cosine of 4t. We then add 10x, so 10a cosine of 4t plus 10b sine of 4t. All of that is going to be equal to 25 cosine of 4t. Okay, if we start with the cosines, we have that cosine, and that cosine. So we get negative 16a plus 24b plus 10a is equal to 25. So negative 6a add 24b is equal to 25. If we look at our sines, we get negative 16b minus 24a plus 10b is equal to 0. So negative 6b minus 24a equals 0. Okay, so we have a system. If I solve for b, b is equal to negative 4a. Substitute that back in. Are you okay if I just tell you what a and b end up being?
Mm-hmm.
Yeah. Okay, a ends up being negative 25 over 102. B ends up being 50 over 51. Okay, so our solution so far is e to the negative 3t, c1 cosine of t plus c2 sine of t minus 25 over 102 cosine of 4t plus 50 over 51 sine of 4t. And then, while that was a long problem, we're not done yet, so please don't stop there. We were given two initial conditions, so we need to find C1 and C2. We were given x of 0 is 1/2, and x prime of 0 equals 0. I'm going to continue by finding the first derivative of x of t. Starting here and doing the product rule, we get negative 3e to the negative 3t, c1 cosine of t plus c2 sine of t, plus e to the negative 3t, taking the derivative in parentheses, we get negative c1 sine of t plus c2 cosine of t. And then don't forget, you still need to take the derivative of those two terms. So we get plus 50 over 51 sine of 4t plus 200 over 51 cosine of 4t. Okay, starting with x of 0 equals 1/2. We get 1/2 is equal to, that'll be 1, this'll be 1, that'll be 0, so we get c1. That will be 1, so minus 25 over 102. That'll be 0. C1 ends up being 38 out of 51. X prime of 0 equals 0. We get 0 is equal to negative 3. This will just be 1 times C1. So C1 is at 38 out of 51. This will be 1, 0, 1 times C2. 0, that'll be 1. C2 ends up being negative 86 over 51. Okay. Final solution ends up being x of t is equal to e to the negative 3t multiplied by the quantity 38 over 51 cosine of t, subtract 86 over 51 sine of t, minus 25 over 102 cosine of 4t, plus 50 over 51 sine of 4t. Questions so far? So none of that was really new except for the setup, the starting point. Okay, few things we need to talk about. What is going to happen to the motion as t goes to infinity? Does the motion of the object deaden? Does it oscillate? Does it oscillate and then deaden? Probably helpful to look term by term. As t goes to infinity, what happens to all of this right here? It's going to go to 0. This will deaden. What happens here? Oscillates. Okay. The part that deadens, so this part right here, the complementary solution, that's called the transient term. You guys have heard that before, it's just been a little bit. If we take the limit as t goes to infinity of that term, we're going to get 0. Transient term means it disappears over time. Okay. The other term, the one that doesn't disappear, so our particular solution, is called the steady state solution. Okay, why does it make sense that we should have a steady state solution? That the motion just doesn't deaden for the entire solution? Because the external force, right? Your external force is moving, so there's no way that the movement is just going to deaden completely. Okay, I want us to look at a few things graphed. So you don't have to do this. I'm going to show you. I already put them in here. That is the arm motion. Okay, so the window probably is not the most helpful. Okay, do you see that the amplitude at the beginning is a little bit higher than the remaining peaks? That's because of that transient term. Okay, so this is all of x of t. It's also interesting if we look just at... You laughing because it took me... Okay, well that was x of t. This next one is just the transient term. Okay, so that's just the transient term. You should see dead ends real quick. Okay, and then this one is the steady state solution. So that's the external force that's working there. Okay. That is the only solving one we're going over together because that's nothing new. That doesn't mean we're done. We still have more notes. But do we have any questions on setting the problem up, interpreting, or solving?
Will the complementary solution always be the transient one?
I'm going to say yes, but I'm like 71% sure on that answer. So. Okay. So, done with that. Next thing I want to talk about is resonance. Do we know what resonance means? Huh? Okay, I'm going to give you my interpretation of resonance. Resonance is when a system oscillates with larger amplitudes at certain frequencies. Okay, so what we're going to be interested in eventually is when our system hits resonance. Before we talk about that, a little bit of interesting history with resonance. Around 1959, 1960, some airplanes were flying, 2 of them specifically, and the wings broke off. So then engineers wanted to figure out like what's going on. Why did the wings break off? Did you guys know that wings on an airplane have a little bit of give? That they're not like strictly stuck where they are. So they have a little bit of give and they flutter. Now what was happening is that the wings were oscillating, the engine was oscillating, and it was too much. And that's what broke the wings off. And that's what the engineers figured out. And so then what's interesting or what we need to know is when does that resonance happen? So when does that happen that the oscillations are too different or too much? So that's what we're gonna be interested in, is what needs to happen for resonance to occur. Here's the equation we're gonna start with. X double prime plus 2 lambda x prime add omega squared x is equal to F naught okay. So what this represents, that is some force that vibrates. Okay, now we need to solve this. In the interest of time, I'm just going to tell you what the solution is. If you're really interested in solving it yourself, you can do that on your own time. Sound good? So like there's some differential equation stuff that's going to happen. And then you're going to come up with the solution. Okay, x of t is equal to a e to the negative lambda t sine the square root of omega squared, subtract lambda squared t, add phi, plus this long fraction, the numerator is just f naught. Denominator is this big long square root. It's omega squared, subtract gamma squared squared, plus 4 lambda squared gamma squared sine of gamma t add theta. Woo. Okay, this one is the complementary solution. This one is the particular solution. That complementary solution, as you can see, is the transient term. Particular solution is our steady state. Bless you. Okay. Yes.
Is the plus b in the sign?
Yeah. Yeah. That's a good question.
All of that?
I'm going to say yes. Yeah. Yeah, I'm pretty confident it is.
And then at the end,
That's a theta.
oh, it is.
This is a theta. That's not a phi. That's a theta.
Yeah.
That's sine gamma t plus theta. That's in the denominator, right?
No. This is the coefficient all times sine. Okay. So we clearly need to know how to find all of these different variables. A is exactly how you found it before. Square root of c1 squared add c2 squared. To find phi, sine of phi is equal to c1 over a. Cosine of phi is c2 over a. Okay. Finding theta, sine of theta is equal to 2, negative 2, lambda gamma, all over that crazy square root. So omega squared subtract gamma squared squared, add 4 lambda squared gamma squared. Cosine of theta is omega squared subtract gamma squared divided by that whole square root. Are you guys okay if I just keep writing square root and not writing all the stuff underneath?
Yes.
Yeah, because it's just the same one over and over again. Okay. So then what we're going to do, this term here, I don't want to have to keep writing out. I'm going to call that G of gamma. Okay, focusing on our particular solution. The particular solution is going to be G of gamma and then sine of gamma t plus theta. Bless you. So we got two pieces here. Like I said, we're interested in resonance. So we're interested in when the amplitude is highest. What piece is going to affect the height of the amplitude? The first one or the second one? First one. Right here, we have an amplitude that's bounded. Here is where a spike could occur. Spike in the oscillations or in the amplitude. Okay, so if we're looking for resonance, larger amplitudes, we're looking for the maximum amplitude, that's going to come from here. What do we do anytime we want to find a maximum? We take the derivative. So that's what we're going to do. Ooh, okay. So, to remind you, this is what we're finding the derivative of. Okay. We get F naught. The power was negative 1/2, so bring that down. We then have omega squared subtract gamma squared squared, add 4 lambda squared gamma squared, now to the power negative 3/2. But we have to do the chain rule, so we do have to take the derivative of the stuff that's inside, according to gamma. So we get 2 omega squared subtract gamma squared times negative 2 gamma plus derivative here. We get 8 lambda squared gamma. Okay. And we need to set this equal to 0. Now, let's be smart. Is this part going to equal 0? Isn't this positive, and isn't that also positive? Yeah, that's not going to equal 0. This part, though, could equal 0. The second part. Ooh, so that's what we're going to set equal to 0. Okay, so what I'm going to do is I'm going to multiply that negative 2 gamma in. Suggestions for what to do next? You see 3 terms. What is your first initial thought? Factor. Okay, we're going to factor. Remember that we are solving for gamma, so we want to factor gamma out. I'm going to factor out a negative 4 gamma. So we get omega squared, subtract gamma squared, subtract 2 lambda squared. Yeah, okay, this is beautiful. First term, we get gamma equal to 0. That is not helpful. Next term, we're going to set equal to 0. Okay. If we solve for gamma, so move everything to the other side, take out the negative, take the square root. We get the square root of omega squared subtract 2 lambda squared. Okay. Now, one thing to remember about this term. Remember that this is part of the coefficient on sine. Which was the driving force. Okay, so that would help us find when the maximum oscillation occurs. Then if you want to find what it actually is, you would have to plug that back in. Okay, here's a few other things I need you to know. The period, when the period of external force is the following: 2 pi divided by the square root of omega squared subtract 2 lambda squared. This is when the system is in resonance. And then remember to find the frequency. It's just the reciprocal.